Why PF drops? Real examples from homes and industries. Welcome. Today we are diving into the physics of electrical efficiency. We often hear about power factor, or PF, usually in the context of industrial penalties or energy bills. But why does it actually drop? In this presentation, we are going to look at the real-world causes, from the appliances in your kitchen to the massive motors on a factory floor, to understand the cost of this electrical inefficiency. Section title. First, let's strip away the jargon and establish exactly what we are measuring when we talk about power factor. What is power factor? At its core, power factor is an efficiency ratio. It measures the relationship between real power, measured in kilowatts, which is the power doing actual work, and apparent power, measured in kVA, which is the total power supplied by the utility. In an ideal world, this ratio is 1.0, or unity. Anything less means your system is drawing more current than is strictly necessary to do the job. It's essentially a measure of how effectively you are converting electricity into useful work. The culprit: inductive loads. So, what drags this ratio down? The primary culprit is the inductive load. Devices like motors and transformers rely on magnetic fields to operate. Creating and maintaining these fields requires reactive power, or kVAR. While necessary, this power doesn't actually turn the shaft or heat the element. Instead, it causes the current waveform to lag behind the voltage. This phase shift is what we quantify as a low power factor. Household offenders. You might not face utility penalties at home, but the physics is the same. Your household is full of inductive offenders. The compressor in your refrigerator, the heavy motor in your air conditioning unit, and the drum motor in your washing machine, these all rely on induction. While the impact of a single appliance is small, collectively, they shift the current phase in residential grids. Industrial systems. However, the stakes are much higher in industry. This is where we see the massive drain. Large-scale three-phase induction motors are hungry for reactive power. Consider this: a facility operating at a power factor of 0.75 is drawing roughly 33% more current than it would at unity to do the exact same amount of work. That excess current creates heat, stresses cabling, and forces utilities to install larger infrastructure, costs they pass on to the consumer. Hidden and high current culprits. It's not just the motors that are running. There are hidden culprits. Transformers, even when idling with zero load, draw a continuous magnetizing current. Furthermore, specialized equipment like electric arc furnaces and heavy industrial welders are inherently nonlinear and highly inductive, often dragging power factor down significantly during operation. Modern challenges. In the modern era, we face a new set of challenges. We have introduced nonlinear loads like variable frequency drives, VFDs, and UPS systems. While these improve control and backup reliability, they don't draw current in a smooth sine wave. Instead, they sip power in sharp pulses. This creates harmonic distortion. While technically distinct from the displacement power factor we discussed earlier, harmonics pollute the grid and complicate our correction strategies. The efficiency trap. There is also a common engineering mistake that destroys efficiency: the oversized motor. There is a tendency to think bigger is better for reliability. However, an induction motor running at only 30 or 40% of its rated load operates at a terrible power factor compared to one running at full capacity. Proper sizing is the first, passive step toward a better PF. Practical example. Let's look at the data. Here is a practical example of correction. We have a 100 kilowatt load. In the red bar, at 0.80 pf, the system demands 125 kVA of apparent power. By installing capacitors to supply that reactive power locally, we boost the PF to 0.98, shown in the green bar. The demand drops to 102 kVA. The real work output is identical, but the wasted current, and the associated cost, is virtually eliminated. Quote. To summarize, think of low power factor as an inefficiency tax. It forces current to travel through conductors simply to create magnetic fields, increasing resistive losses and demanding larger infrastructure at every step of the grid. Q&A. Understanding the cause is the first step toward correction. Whether it's sizing motors correctly or installing capacitor banks, the goal is always efficiency. Thank you for watching, and I'm happy to take any questions you might have about optimizing your power systems.